So good morning, everyone. For those who don't know me, my name's Robin Lee from the University of Canterbury, and today I have the pleasure of introducing our QuakeCoRE seminar speaker, David Dempsey. David is a senior lecturer at the University of Canterbury, actually having recently moved down from the University of Auckland, and his research focus is pretty broad, but I think generally you'd say that he deals with advanced computer modeling of energy and natural hazards problems. So today, David will be talking about the synthesis of three things that I really like: artificial intelligence, ground motion simulations, and Italian cuisine. So with that, David, the floor is yours.
Thank you, Robin. The purpose of this talk really is not to go super deep on any one particular application of AI. It's really to give you an idea of the changes that have been happening over the last few years, and to focus on a few areas where AI can really contribute, not just to ground motion simulation, but really to any kind of modeling. So in that sense, I'll be kind of taking a high-level approach, highlighting a few things that have been done recently in the literature and a few works in progress. So we should start, I guess, with some definitions, and we'll start with artificial intelligence because it is a bit of a catch-all buzzword that gets thrown around far too much. And so some formal definitions will be quite helpful, I think. So maybe I'll just give you a moment to read this passage quickly. So probably you're still halfway through it, but this was written by an AI called GPT-3, which is a natural language processor. It is a computer program that was fed a whole bunch of text written by humans and has tried to learn the patterns and mimic what people do when they write text. And the way it works is you give it a little snippet to work with. I've given it what is the future of earthquake modeling. And GPT-3 has come up with the rest of these two paragraphs. And I think you'll agree with me, in a sense, it is mimicking human intelligence. It is, it's capturing sentence structure fairly well. There's even an evolution of ideas throughout the two paragraphs. Unfortunately, it is totally bonkers nonsense. So there's also some shortcomings, and the mimicking human intelligence is still a long way from being actual human intelligence. So that's one definition of AI, is just any kind of program that is attempting to mimic what people can do. Another definition is that it's sort of machine or computational capability at things that are at the bleeding edge of what humans can do. So back in the 90s, this was creating a computer program called Deep Blue that beat this guy here in chess, Garry Kasparov. And it did it through basically a brute force algorithm for coming up with possible strategies that might beat him. These days, that's not really considered bleeding edge. You'd think more about maybe a self-driving car. And so here it needs to take in a whole bunch of data, visual data, identify hazards in the road, make decisions about what the best path is forward, interpreting all of this information. And that's kind of the next bleeding edge task. So this leads to a second definition of AI, which is that it's really a bit of a moving target. It's the things that we can't yet do with computers, so no longer chess. And actually, once we can do them with computers, some would say it's not really AI anymore, which is unfortunate, especially if you are describing your recent research paper as AI. More specifically, artificial intelligence is sometimes technically described by artificial neural networks and deep learning, words like fuzzy logic and heuristics. So these are some of the more computational approaches that are sometimes used. And an endless source of lazy jokes about pop culture references, which I need to just flash up briefly and move on from. So why do you keep hearing about AI so much? I have gone through and looked at it. It's been around for a while, of course, since the 1980s and before. People have been talking about AI. But really in the recent 2000s, it's taken off, and since 2015, and its currency is really appearing to skyrocket. And so there's clearly a lot of interest and a lot of perceived value in AI in terms of whatever it is it can do. Much like other well-known, potentially well-known bubbles in history. This is one of the greatest time series I think I've ever seen, going back a long way to the 1600s. So that's an intro into what AI is. I want to talk now about 3 things that AI can theoretically be good at doing for you. And the first is automation. And the thing to think about is, those little machines that we order off at McDonald's now, those big boards that replace the people up front, or maybe the self-driving cars that mean you no longer have to interact with human beings when you're coming home from the airport. So why would we want to automate things? Of course, it's because we never have enough time. And particularly when there are repetitive tasks and maybe they don't require much of your brain power because you are quite specialized at doing them and they're easy for you, wouldn't it be nice to get a computer to do it? In terms of the how, this is usually done with something called a neural network. A neural network, and there are lots of different flavors and varieties of them, is just a class of imitating functions. So it's just a kind of computer program that is really well specialized on imitating, at learning patterns and then reproducing them. So it involves a lot of training and teaching, but once if you invest that effort up front, it does a reasonably good job with a good degree of accuracy. Let's look at some examples. So consider earthquake detection and what a trained, skilled operator might do. So they'll see a little time series and it looks like this. And they might look at that and say, yes, that's an earthquake. I know what an earthquake waveform looks like, and that's 1. They'd also be able to say, look, here is the P wave. I know it's the P wave arrival because it's where the signal starts to increase earliest in the sequence. And it comes before the S wave, and this is where I think the S wave is roughly. This is a bit of a noisy signal, so it's a good example. So recently, last year, there was a publication that has sought to automate this using a large neural network. This is a visualization of that neural network. And what they've done is they've taken this computer program and they've trained it on 1 million earthquake waveforms that have already been picked by human experts. And that's a common thing you'll see with these artificial intelligence approaches, is that they actually require a large amount of upfront work by other folk to create, in this case, what's called labeled training data. Now that is fed in at the top to this neural network, which is just a sequence of sub-programs that are really chopping up that data, reducing its size, trying to extract the important patterns, and then later reconstructing it here into things that it thinks are important features of that data. So things like, is there actually an earthquake? When did the P phase arrive? When did the S phase arrive? So that's the convolutional neural network. And the output in their case is some probabilities or some probabilistic envelopes for those things. So for their model, it looks like this. The output of the EQ transformer is for detection, this sort of window where this is where the computer program thinks the earthquake is, or the wave train. This is where it thinks the P wave arrival is. You can see there's definitely a density around where the genuine arrival is, but it gets a little bit confused. And this is where it thinks the S wave is. Again, not a solid discrete pick, but maybe more like a probability distribution. And so one of the one of the pillars of AI training is this idea that it's all very well to try and fit it on some data, but you want some idea of how genuinely it's performing on data it's never seen before. So this is generalization. And these guys, what they did is they trained on, these 1 million waveforms, and then they reserved 42,000 of them in what's called a testing set, and then tried to see, all right, this complicated computer program that has in theory learned the patterns, how does it genuinely perform on these earthquakes it's never seen before? And its picks are reasonably good. Within about 6 samples, if you're at 100 hertz sampling rate of the human picked arrivals, which is pretty good. Now, in the ground motion space, there's been some recent work here at Canterbury looking at classification. So this is the idea of sorting into different bins, in this case, a good and a bad bin for quality of ground motion records. So again, if you're a skilled operator, you can look at this and say, yes, it looks nice, it's got low noise. Oh, this one's not so great, it's got a reasonable degree of noise. I can see it's good and bad. What we'd like, though, is that, these days we're putting out more sensors. Suddenly there's a lot more data, and it might require someone working, 6 months to get through it all and classify it. Wouldn't it be better to teach a machine to do it and to run through it in 5 minutes? So Xavier's been working on, or has published a couple of years ago, on these neural networks, which again, just take inputs, chop those inputs up and rearrange them in ways that can generate an output, in this case, a quality metric, where the inputs might be some ground motion records. Mike's also doing some work on this with a bit more of a complex neural network, but again, similar kind of concepts, just trying to reduce information, extract key patterns, and then rebuild some sort of estimate of the quality label and some frequency information. And in terms of performance, Xavier's, I think you'd say, did quite well. Here it is selecting different records that it assesses to be worthwhile going forwards with. And what you're looking at here is that it's selected a lot of records that a human operator has classified as high quality. It is selecting not many, but definitely some records that a human operator has classified as low quality. So not perfect, but pretty good. And when those are fed into ground motion simulations, shockingly, you find that going from black to red here, black includes all those low quality records, red excludes them. We're seeing generally an improvement in the ground motion simulations and their ability to match the data, because now we're focusing on the high quality data and less on the poor quality data. So seems to be an improvement. That's automation. The second topic I want to talk about is acceleration. So this is the idea of speeding up computer models using AI. Now, the motivation for this, many of you will have heard of or be familiar with this idea called Moore's Law. It was proposed a long time ago, and it was essentially a recognition that over time computers get faster, but they seem to get about twice as fast every 18 months. And we see this, there are a number of ways you can measure it, the number of transistors we can cram into chips, performance of single cores, the number of cores we can use in parallel with each other. All of these things are sort of increasing according to these nice laws over time, power laws. So that's Moore's Law. Computers are getting better. And of course, the modelers have responded by, as you would, as a computer gets faster, you just make a bigger model with more blocks. So this is an example from the geothermal literature, looking back over 40 years of data. The number of blocks we've been running in a model of, I think this is the Wairake geothermal system, has been increasing over time, almost in lockstep with the evolution in computing power. So how are we responding to better computers? We're running bigger models. And the result is that in 1980, a computer model took about 4 hours to run. And today, a geothermal model takes about 4 hours to run. because instead of using that additional computer power for other things, we're just building bigger models and settling on a tolerable runtime of about 4 hours. So is there a better way we can speed up our simulations than just building faster computers? So this is where the AIs come in. This is an example of an AI. I mentioned before that AI are really good at imitating. So they can imitate what humans do. They can also imitate what computer models do. This is an example of a Navier-Stokes fluid simulation. So Navier-Stokes is a complicated equation describing how fluids evolve over time. It's reasonably difficult to solve in a computational sense because you get things like turbulence. You need quite small grids. On the left here is an example of that physics simulation, and on the right is an imitation of it evolving over time with an AI. And the key here, I mean, I think you'd agree that they are largely similar to each other. The key here, though, is that the AI is about 1,000 times faster than the physics model. So that's what we're getting, real good speed up without much of a cost in terms of accuracy. So how does this work with physics-based ground motion models? And this is where I can see Robin starting to get excited because we're talking about pasta. One way to think about a ground motion model is as making ravioli. And this will be a very tired and stretched analogy by the end, but you'll have to bear with me. So we've got a physics-based wave equation, and that's kind of like your pasta. It's the structure that gives meaning to everything else. Then we also have some way of solving that equation, some way of taking that and turning it into something else. That's our simulator, or pasta maker. It's our simulator. It's got all the grids, it does the finite differences, it does the time stepping. There's a whole bunch of computational stuff to take that wave equation and turn it into something meaningful. And really what makes or breaks or makes your pasta interesting is the filling. So the filling is the specific location information. Things like where is the fault, how long is it, what kind of ruptures am I expecting on it in terms of hypercenter, stress drop, slip, that kind of thing. So you take that information, you pair it with the wave equation, you crank it through the simulator, and what you get out is a delicious ground motion intensity prediction that looks something like this. So it may be more intense in some locations, less intense in some others. So that's great. Another way to think about this is just an input-output machine. It takes those inputs, it does something in the middle, maybe a bit of a black box, except for the guys at QuakeCoRE and the software guys, and then it produces an output, which is useful. But thinking about this as an input-output machine is useful as we go forward. We can change the flavor of the pasta simply by changing the inputs. So we're not changing the wave equation, we're certainly not changing the simulator. All we're changing now is looking at a fault, Kitapehi fault in the Hauraki Rift. We chuck that in, crank the handle, and you get another ground motion intensity prediction, a different flavor, but largely the same process in terms of creating it. And that's what I want to highlight here. This thing really doesn't change. It's the same each time. So wouldn't it be nice if we just focused on that and we made it faster? And that's what this is. We're going to replace the physics-based ground motion simulation with a deep neural network. And this is a visualization of what that is. A deep neural network takes those inputs, so the fault locations, hypocenters, stress drops, that sort of thing. And then it just chops and changes and recombines them in random ways, multiplies, adds, subtracts, whatever, and it keeps doing it, chopping it into all these unrecognizable intermediate products until at the end you get something else that looks like a ground motion intensity prediction. And the key is in the training of this thing. What you need is a lot of input data with a lot of known output data from your physics simulator, so that when you're tweaking all of these little branches in here and recombinations, it knows what it should be aiming for. And that's this ground motion intensity prediction. So we'll fire in tons of training data on the left and right hand side here. And we're trying to tweak these weights in here so it's a reasonably good, the output of this is a reasonably good approximation of these physics ground motion intensity predictions. Then you come along with something else it hasn't seen before. So this case, the QuakeCoRE earthquake and the inputs for that. You pass that into the neural network and it will spit an output out. And you ask the question, does that output of the network look like what my physics simulator says it ought to be? So that's the key step of testing your neural network to see if it's actually any good. Okay. How are we going with this? Claudio has been working on a deep neural network for all of New Zealand. They've been using the CyberShake input data. So this is all the faults that simulations have been run on. This is a compilation of all of the outputs of those. In reality, what we've got is hundreds of individual simulation inputs on the left, hundreds of individual simulation outputs on the right. And we're just tweaking these weights in the middle here to try and get as good a match as possible to the physics simulator inputs giving outputs. So that's the training. In terms of the testing, here's one example of an earthquake. If you look at these, I think you'd agree with me that it's capturing first order effects to a pretty good level of detail. It's capturing these high intensity ground motions here. I should mention on the right is the neural network, on the left is the physics simulation. In this case, it's a work in progress. They're still missing some key things. They're missing second order features. Probably wouldn't feel second order if you're standing in Nelson, but it's missing some of these basin effects here that have got a smaller spatial scale than the large, I guess, footprint of the fault here, also around Christchurch. So still some work to go. But in terms of what you get, this took 188 core hours on Nessie to run, so 188 hours on a laptop if you were running it on a laptop. This one only took a second, which means you can generate massive numbers of these. You can do them quickly after you experience an earthquake to get an assessment of what the possible intensity maps were. So that's the real strength here. Another one my group's been working on is something called adversarially constrained autoencoder interpolation, which is an unnecessarily complex name for just merging two pictures together. So the idea here is you take two images and you're looking to interpolate between them in a way that you could look at any of these images and say, yes, that is a credible image of whatever. In this case, it's faces. We're looking to do it with intensity predictions. So it's an adversarial model, which means really you have one network that is taught to do the blending, and you have another network that's evaluating your first one. The first network is trying to trick the second network into believing that what it's producing is a credible face or a credible ground motion prediction through interpolation. It's a bit of a complex and contrived setup, but it tends to produce very good, well-trained networks. So here's an example, just looking at ground motion simulations from the physics model for two differently sized earthquakes on the Kiripehi fault, a 6.6 and a 7. And then we use this adversarially constrained autoencoder interpolation to try and do some sort of feature extraction and then interpolation between the two. And we come up with something that looks like this. Certainly not perfect. I think it's probably underestimating at the short end here. But this took about a second to generate. Each of these took, maybe 50 core hours each. And it's clearly extracting some of the spatial location features and, in a sense, interpolating or blending between them to generate this output. So work in progress, but I think it has promising aspects. So just reflecting on those 2 points, the automation and acceleration. I think these will be increasingly justified as we see volumes of work continuing to grow and grow, and that volume of work could be because we've got more sensor data to work through. It could be because we've got more simulations to run. So the motivation there is clear to me. However, it's also clear that a lot of times the accuracy for these methods is going to be lower than what a human operator or a physics simulation would achieve. I've tried to show you a couple of examples of that. And so really there's a trade-off there to be accepted. Will you accept lower accuracy given the potential speed ups and burdens that can be relieved by these techniques? You've also got a significant upfront R&D cost to get these methods developed, tested, and operationalized. I would argue that is true for almost anything, including physics-based ground motion simulation, so that necessarily shouldn't be anything that's off-putting, but it is there and something that you shouldn't think these will be quick fixes that can be implemented by just training a PyTorch model. And then lastly, in my experience, these methods tend to attract a lot of skepticism and mistrust. Sometimes it's warranted, often it's not. In some circles, there's an allergic reaction to the words AI and machine learning. Like with anything, let's be fair and balanced with our skepticism and hold them to a high degree of standard. That means evaluation. And the evaluation period might be more protracted with some of these methods. So just some things to think about. Lastly, a really cool topic I think you can get stuck into with AI is the discovery of patterns, new patterns that you might have missed. And this is because these methods don't get tired, they're happy to work overnight, which means they're really well suited to brute force. If you think a little bit about the scientific method, or the classic scientific method, the idea is that you go out and you spot something new or weird, you come up with a hypothesis, and then you test the hypothesis. So an AI is a little bit dumb in the sense that it can't go out and spot something new or weird, but it can come up with hypotheses as long as they're simple, and it can test them very rapidly. So that's what we do, or that's one thing we can use an AI for, is inventing and testing hypotheses very rapidly. Here's an example for empirical ground motion equation discovery. You can take a ground motion equation, like this one here. It contains 1, 2, 3 terms at the top. Ignore the bottom line for now. And you can represent it as a tree. So if I look along this branch of the tree, it's the quadratic term here. It's a constant multiplied by the magnitude. Here's the multiplication. And it's one branch higher multiplied by another term, which is the magnitude. And that becomes the term on the right-hand side. So it's just, this tree is really just a representation of the grammar in these equations. Once you've done that, you can train up an AI to go through hundreds and thousands of these trees. So you jumble them up, or you try lots of different varieties, but you can evaluate tons and tons of them against the data, and really quite inventive ones. And that's what these guys have done. And in the end, they decided that this was their favorite ground motion prediction equation, the one that minimized the misfit with the data the most. And it contains some, pretty inventive terms in there. Another really cool topic is on earthquake prediction. Now, I don't expect we're going to be predicting earthquakes in the wild in the next 10 years, but these guys have looked at some very interesting signals in generating lab earthquakes. So a lab earthquake is generated essentially by clamping a slab of rock in the normal direction with 2 layers of fault gouge in it, and then pushing it in the out of plane direction, generating increases in shear stress and then sudden drops, which are your earthquakes. So this is kind of classic stick-slip behavior. What this experiment does is it generates these very long time series of, in this case, strain, with these very distinct lab earthquakes appearing. What they then did is decomposed that raw time series into different properties. So things like the instantaneous or local variance, how much wobbliness have we got in the signal? things like the kurtosis, threshold. There are hundreds of these time series features that you can extract from the raw time series that are just giving you an indication of one aspect of the data. You can take those and model the time to failure, and that's what they've done here. So the time to failure in this case can be a known quantity. It decreases in red over time until an earthquake occurs, and then it jumps up. The blue shows the model responding to that time of failure or trying to predict the time to failure. And the key point is that this is an out of sample prediction. This is the model on data it hasn't seen before and is doing a reasonably good job in blue of seeing that an earthquake is imminent and capturing when it is likely to occur. So whether or not you believe that, one of the nice things you can pull out of those features is when the different features are important and how they translate to physical phenomena. So here now they are highlighting which physical phenomena are important at different times. When you're a long way from failure, they're highlighting that the diagnostic elements of that being a long way from failure are these tremor-like signals with high amplitude. Whereas when you are close to failure, their model is responding more to these impulsive signals. So it looks a bit more like a characteristic wave train, not precisely, but what this approach is doing is highlighting which patterns in the data are significant and important and worth your thinking about from the perspective of maybe constructing a physical hypothesis. So I thought that was really cool. So I'm at the end, so let me summarize. Artificial intelligence, by some people's definition, will never be achieved, and nevertheless, it is driving a whole bunch of development, not just in ground motion simulation, but across the sciences. First of all, it automates things, and that gives you lots more time to work on other potentially equally boring tasks. It means your simulations are much, much faster, so that the uncertainty analysis that you keep talking about as important but never actually bother doing, maybe you'll finally have an opportunity to do that. And then really physics discovery is an exciting new aspect, I think, of these tools, particularly their ability to look for brute force patterns. And so I thought I would finish this talk by giving the last word to GPT-3.
All right, thanks for the fantastic talk, David. I assume everyone's finished reading as well because I'm known to be a very slow reader. So I guess I'll open it to the floor. Does anyone have any questions for David? Okay, I guess I'll start and give other people a bit more time to think. A while ago, David, I saw that you presented some stuff that were artificial intelligence predictions of ground motion simulations for more simple models, more simple fault models. I think it was like a point source from last year or something.
Yep.
Curious to know what kind of differences do you see in the ability of these artificial intelligence to predict a simple source model versus a more complicated one?
Yeah, I know the one you're talking about. So that was trying to emulate viscoelastic deformation around dislocation models, which is another kind of earthquake problem. It's a good question. If I can scoot all the way back. So you saw I was showing almost there, past the pasta. This one here. So clearly we can get an AI to replicate this, and I don't want to call this a simple problem. It's clearly not a simple problem, but it's also a 2D contrived case. You know, typical use cases for fluid mechanics simulations are modeling airflow around aircraft. They're not doing that here. or modeling atmospheric turbulence. They're certainly not doing that here. So there's a genuinely good question about how well will these approaches upscale from toy problems, which they seem to be performing quite well on, to real meaty sized problems. Perhaps, I mean, some of the best evidence I have seen has been Claudio's work here. You can see this is certainly not a toy problem. This is a real life problem. And we're seeing evidence that it is capturing first order features without, reasonably accurately. It's these second order features that may be important. And I think the outstanding question is whether or not it can be, or what the best way is to teach it to value and capture those as well. So yeah, an open question, and probably at least decades worth of work.
Thanks. Any questions from others on the line? Okay, we have a question in the chat. Are we sure that the filling of that pasta is legal?
I don't know what that means.
I don't know, what did you put in the pasta? What was in the ravioli?
Oh, just ground motion simulations. Yes, you do want to, look, if you're training one of these models to imitate a ground motion, physics-based ground motion simulator, you don't want that to be flawed. Otherwise, you're going to inherit those flaws into whatever your artificial intelligence emulator is going to be. I think you guys have worked all the bugs, though, out of the Graves and Pataka by now, right?
Depends what you mean by bug. Okay, I have one more question. So these AI predictions are based on a model itself. There's the age-old question of model predicting model. What do you think is the true bottleneck towards actually making a good prediction of an observation if you're going to use this AI method? Is it the validation of these models against data, or the actual ability to train these neural networks? Or both, probably both, but your thoughts.
Yeah, no, I know what you mean. It's one thing to say, we need to build the computational architecture for a complicated neural network. I think that has largely been, I don't want to say it's done, but in terms of the thing that's lagging behind, I think it's more on the validation side of things, as you say. So a great concept in machine learning and AI, which is increasingly penetrating, I think, into traditional modeling, is the idea of cross-validation. The idea that you reserve a test data set that you calibrate or train your model on only a subset of all the available data. And then you later say, all right, well, how well does it perform on the test data that in theory it hasn't seen? Of course, you've seen it because you were training everything in the first place, but maybe the model doesn't. And that, I think, gives you the best estimate of how valid is the model. Otherwise, we end up in a situation where we just say, look, what is the best model we can get that fits through all of the data, with no sense whatsoever how much we're fitting the noise, how it's going to perform in the future.
Yep. Good answer. All right, one question on the line. How do we approach the human bias when training neural network models with human model data?
That's a good point. So simply speaking, you couldn't expect to incorporate that human bias into your AI trained model, I think. So probably whatever methods you would tend to apply to your physics-based model ought to be equally applied to your AI model if you are looking to identify and eradicate those sources of bias. I mean, you can just, if you like, you can just look at AI models as another way of solving differential equations. And in fact, there are plenty of neural networks out there that are constrained by differential equations. So part of their training routine is to imitate the differential equation as much as possible. And if you're imitating a differential equation, genuinely, what is the difference between solving it and imitating its behavior? I'd argue there's not a lot of difference. So in that case, these models aren't so different from what we're already doing in some cases.
Leveraging off that question, I guess, what are your thoughts on then not removing human bias, but removing user bias by actually having inputs from multiple people rather than just one person doing the labeling of data?
Yep. No, I think that's great.
Okay.
I think that applies to all models probably, yep. And something that is worthwhile doing.
Yep. Perfect.
Absolutely.
Okay. Any last questions? We're just heading up to slightly overtime. If not, then I'd like to give David a virtual clap. Fantastic presentation. And I guess there'll be another one of these calls in 4 weeks from now. Thank you everyone for coming today.